end of this class. That's good. 3 more lectures, and then we finish. This job is better. Let's see. Let's have a nice discussion today. This is lecture 18. So a little bit more about Hilbert spaces. So I have made a little change in our calendar. Next week I am changing with the tutorial. So we're going to finish this course next week. I'll say, okay, so our next classes are going to be next Wednesday at 11 a.m. and the regular time Friday at 4 p.m. Okay, so Wednesday at 11 was going to be the tutorial of Wagner. I changed with him, so we finish next Friday at 4. And then Wagner will take my spot on the next Tuesday, the regular time. Okay, and our exam, it's going to be on the, if I'm not mistaken, April 24, right?
Yes.
In the morning. So just reserve on your mornings, from 9 to 12 or 9:30 to 12:30. Still to be decided. Good. Okay, so last class we started discussing a little bit about Hilbert spaces. And so for me, Hilbert space H is a Banach space with the norm U coming from an inner product. So you have an inner product and you have the norm of U as the norm associated to this inner product. We've seen a little bit about projections. That in this space, if you have a closed and compact, closed and convex set, there's the unique point that minimizes the distance. If this set happens to be a subspace, you have a linear projection map, and we have also seen the, let's say, Rees representation theorem. Since this space H is reflexive, we could essentially show that every functional is the inner product with somebody in the space. Okay, so today I want to lead the discussion. Let's start discussing a little bit about, say, bases and what we call orthonormal sets of bases. And also what we aim to be doing here is essentially to show that every separable Hilbert space is a little L2. Okay, so let me write down a few statements here, and then we can discuss. But the class today will be pretty much standard. So let me say, I'll write down some statements and we're going to prove. So let me follow the book on this definition. So I will have, say, let En and be greater than 1, okay, be a sequence of closed subspaces. Okay, we say that H is a direct sum or Hilbert sum of ENs if, first, these spaces EN are mutually orthogonal. That is, if you have U and V in different guys, their inner product is 0. And the span of the union of all of these guys, if you get the closure, then you get the whole space. So So the span is dense on H. Okay, so recall, remark, whenever I talk about the span of a set, so X, I mean finite linear combinations, okay? Of elements in X. Okay, so let's investigate the situation where I can write my Hilbert space H as a direct sum or Hilbert sum of closed subspaces. And I'm going to write like this if the spaces are mutually orthogonal and if their union spans the Hilbert space. Okay. All right, so let's prove the following statement.
But it's not the closure of this band is the Hilbert space, right? Not this band, so.
The closure of the span is the Hilbert space, yes. The span is dense. So let's prove this following theorem. Theorem, let's just say, assume that I'm going to write my space H as a sum of subspaces En. Given U belonging to H, let's define Un to be the projection of U over the subspace En. I have already defined what's the projection of a vector over a subspace, a closed subspace, right? We have already defined that. And let Sn be the sums of the UKs, k from 1 to n. Some of the projections. And claim the limit of Sn when n goes to infinity is equal to U, and sum of the values of UK squared this is what's called Parseval's identity. Let's do this. Okay, so I'm assuming that I'm writing my H as a sum of closed subspaces, a direct sum, meaning that they're mutually orthogonal. This is what the symbol is, and the span of the union is dense in H. Given H, let us define the projection Un, and let's take the partial sums. Sn is the projection of UK up to n. What I claim to you is that these guys go back to U. When I say the limit of Sn goes back to U is of course the limit in the norm of the space. Okay? And the sums of the squares of the absolute values of these guys is just U squared. That's what we call Parseval's identity. Now, okay, before we go, we'll prove this. Let's see if the following lemma helps us, and then we can discuss together. Why am I going to have this lemma? So, assume that, say, Vn n bigger or equal than 1 is a sequence in H such that each terms are mutually orthogonal, and the sum of the VK's squared is finite. Define Sn to be like the partial sums. Okay. Then S equals to the limit of Sn exists, and norm of S squares is the sum of VK squares. Yeah, this is what I want. Okay, so this is a lot like linear algebra. Let's see. Let's have these two statements in the board, Let me comment on this, and let's prove this on this board. Let's see if this is enough. Okay, so this is pretty reasonable, right? Assume that we have a sequence in a Hilbert space that is mutually orthogonal. It's almost like you think it is a basis. Assume that the sum of the squares is finite. Now define the partial sums of this sequence as n is from sum of vk from 1 to n. What I'm claiming to you is that this Sn, the limit exists and it's S. And the norm square of this limit is this number here. It's a finite number. To prove such a thing, proof of the lemma. It's not
We
very...
take En to be generated by Vn and our H to be their direct sum and apply the theorem.
We are going essentially to apply, well, we're going to prove this lemma, which is kind of a baby case for this, right? It's an easier setting. And then we're essentially going to apply with the UNs will be mutually orthogonal here. Okay, and then morally it's going to be this thing. Let's see. So if you have such a thing, what you do is, well, first you observe what is S, so say let n be bigger or equal than m, and you tell me what is Sn minus Sm. So the partial sums. This is just going to be the sum of Vk from k m plus 1 to n. Right? So, therefore, the absolute value or the norm of this guy, square, since these guys are mutually orthogonal, when I take the inner product of this guy with itself, there will be a lot of zeros, and just this thing here is going to remain. Does everybody agree? Sum of the squares of the... But now, since the whole sum from 1 to infinity is finite, if I take m and n very big, I can make this smaller than epsilon if n and m are bigger or equal than bn, if I want to. So this essentially means that my sequence Sn is a Cauchy sequence in the norm. Since it is a Cauchy sequence, of course, the limit of Sn as n converges to infinity exists, and we call it S. Okay, this limit exists and we call it S. Now what? I have to turn off my phone, otherwise we're going to get some messages here. Let's see. Good. Now it's no big deal. The norm of Sn, now, observe that the norm of Sn squared is just the sum of Vk squared from k1 to n. Okay? And then you pass the limit as n goes to infinity. The norm of Sn squares will obviously converge to the norm of S squared if Sn converges to S, which is just going to be equal to this sum. Okay, so this is the lemma. Let's see if we can apply to prove this theorem. Do we have space here? This concludes the proof of the lemma. Questions? It's okay, it's pretty much standard stuff. How would I apply this to the situation? So perhaps we should think about my UN will be this sequence Vn. Right? So if I wanted to apply this lemma that we just proved into this situation, my UN will be the Vn, right? So UN belongs to the space En. Since the spaces En are mutually orthogonal, UN would be orthogonal to UM. Let's check. Right? And I have the partial sums, like I had here. I want to conclude that the partial sums converge to somebody, and that this norm holds. I don't have yet that the sum of the squares is bounded. of the UN. So this is what we have to show to be able to use that. So it's pretty much this. But on the other hand, the difference here is that here you just started with a sequence of vectors and blah, 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 you got the conclusion. Here you start with a U and H. Okay? So this is what you want to do. So let me just blah, blah, blah. Let's try to do it right here. Proof of the theory. Let's start here. Then we see if we need to change. So the first thing to observe, it's clear that UN, orthogonal UN, is 0. If n is different from n, right? They are mutually orthogonal because this guy belongs to the space En, this guy belongs to the space En. Okay. Now, one thing that we have to do is that from the definition of the projection, you know, projections do not increase the distance. We have seen that, right? So, in a sense, so U minus UN against any vector W is 0. U minus the projection in the product with any vector in the space where you are projecting is 0 by the definition of the projection, right? So we can just take U against UN itself. This is going to be 0.
So if y is w is 0 again?
This is the definition of the projection, right? U minus the projection of U in a space K against any V for any V in K. Okay? Projection we have seen is characterized by this. It's the only guy that verifies this equality for all V's in the space K. Anyway, so you have U minus UN, scalar UN is 0. So in other words, this implies that what do I want? This would imply that, say, this would imply that U scalar UN is actually equal to UN scalar UN, which is UN squared. Right? Okay. If I add these up, if I add this from, let's just put a K here, K, 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 K. So if I add this up from K1 to the N, what do I get is on this side is U, Sn, partial sum. This is just equal to the sum over the UK squared, K1 to N. Good. Does this help me? Almost, right? I'm going to erase it. Still, I wanted to show that the sum of the squares here is finite. Okay, I haven't shown that yet, but let's see how we can do that. Let's see. Now,
It's enough to show that Sn is Cauchy, because if it is Cauchy, then Sn converges to something, and when we take the limit, we can, by continuity of the inner product, we can take the limit as.
Yeah, that is enough. That is enough, but you don't want to be. This, I think, will go into a cyclic argument. But yeah, you can try to prove that. It's not much hard. I mean, it's just to observe that whatever we have here on this side is actually equal to the. So recall that Sn is just the sum over the UKs from 1 to the n, right? So since these guys are mutually orthogonal, Sn squared is just going to be sum over UK squares. From 1 to 8. Do we agree on that? So, okay, so I have here norm of Sn squared. Okay, so this is the magic identity that we get. So U scalar Sn is just equal to Sn squared. And now we're done, because we use Cauchy-Schwarz here. This is less than norm of U, norm of Sn. So in some sense, I cancel this guy, it's bigger or equal than of Sn. Which makes sense, right? Because what I'm taking here is just projections over the subspaces and adding them up. I should get something smaller, and this is the proof of this. So this is always less than or equal than U. Okay? Which obviously means that U squared is bigger or equal than Sn squared, which is equal to this. Okay? So this is what I told you. This number here is always less than or equal than the norm of U squared. Here you have U given vector. That therefore, this implies that the sum over UK squared from 1 to infinity is finite. It's actually less than this number. Then you are in a position to use your lemma. Okay, so from the lemma, this partial sums converge to somebody. This converges to this S. And the norm of S squared is equal to VK squared. Okay. Now, we have to check that S is U, and then we'll be done. Okay, from the lemma, limit of Sn when n goes to infinity converges and goes to a certain S. Okay, we have to show that S is equal to U. We must show this is where the hypothesis of this guy's, the span being dense, enters. Okay, so how would we do that? You see, you go.
Calculate the norm of U minus S and show that it's less than any epsilon.
Say that again.
We calculate the norm of U minus S. And
You calculate the norm of U minus S.
So we get U minus S equal U minus Sn plus S minus Sn. Sorry, I mean I will just use the triangle inequality and put Sn in between.
Let's try to do this. So you propose to calculate the norm of U minus S, right?
Yeah.
How would you do that?
Is less than or equal to the norm of U minus Sn plus the norm of S minus Sn?
This goes to 0.
Yes.
This is what you want to show that goes to 0. So this is just a rephrasing.
Yeah.
Okay,
Sorry.
no problem. I want to show, let us try to show that U minus S is U minus S against V is 0 for any V in the space En. Claim. Let's prove this claim. U minus S against any V in En is 0. How do we do that? Well, let's go again to the box. It is clear that U minus Sn, so if you are saying En, U minus Sm against V is equal to 0 for any V belonging to En when M is bigger. So if M is bigger, what I'm doing is that, remember, U minus Um against V, U minus Un against V was 0 for V in this space, En. I'm taking out the projection. And what is Sm for any M bigger? I am putting more guys, right? So this Sm here, if you look, is just u minus un, and then you have minus u1 plus u2 plus un minus 1 plus un plus 1 plus un, right? This is 0 because u minus un against v is 0, since v is in this space, and these other guys are all orthogonal to the space En. Okay? So I get this thing here. U minus Sm in the product with V for any V in En is 0, provided that M is bigger than N. As long as I take out the projection Un, I'm okay. Good. Now you take this expression here, star, and you send it to the limit when M goes to infinity. And you send it to the limit. When you fix V, and you send M to infinity, of course you get U minus S, scalar V is 0 for any V in En. Well, but now U minus S is a fixed vector. Since you proved this for any V in En and any guy, you can take just any sort of linear combination of En. So this implies that U minus S, scalar V is 0 for any V in the span of Ens. Span of the union, if you want. And obviously, you can actually pass the closure if you want. If U minus S scalar V is 0 for any V in a certain subspace, it's also 0 in the closure. But then we know that the closure of this span is the whole space H. So you're saying that U minus S scalar V is 0 for any V in H. What is the V that you could take?
U minus S.
U minus S, yes. So just take V, U minus S, and conclude. Right. Good. Imply that U minus S squared is 0, if you imply that U has to be equal to S. Okay? So this is not very much difficult, but you just have to do the steps in the right order to get the pieces in the right places. Okay? So we have actually proved that, well, Plancher's Parseval's identity. Is that okay? Good. Okay, so now perhaps we should go to the main statement in this sense. How we are going to use this. Let's see. We want to identify it like this. So, definition, say a sequence En, and from 1 to infinity, containing H, is orthonormal basis of H if it verifies the following properties. First, each absolute value is 1 for each N, and they are mutually orthogonal. And second, if the span of this ENs and going to infinity closure is H, if the span is dense in H. Okay, so I'm going to say that this is an orthonormal basis of H if this happens. Each guy has norm 1, they're mutually orthogonal, and their span is dense in H. So corollary is the following. Good. Let me write here. So I should write from the other book. right here. Let me write right here. Corollary is the following. So let Bn be normal basis of H, then for each U in H, we have the following. U is actually the sum from K from 1 to infinity of U scalar Ek times Ek. So this is just the usual decomposition, and U squared is just the sum of U Ek squares. Conversely, if alpha n is a sequence in little L2, the series sum of alpha k Ek converges to an element in H such that U with Ek is equal to alpha k, and U squared is just the sum of Ek squares. This is essentially the isomorphism that I was talking about. So if I have an orthonormal basis, any U in the Hilbert space can be decomposed in this basis. Okay, it's the sum of U scalar Ek times Ek from 1 to infinity, meaning that this is actually, this means, don't forget, this is actually equal to the limit when n goes to infinity of these guys, okay? U, Ek, scalar Ek, K from 1 to n. Okay, so when I say it's the limit from the sum from 1 to infinity, I don't mean it in a pointwise sense. Of course, I mean it in the limit in the norm of the space. This guy, these elements of the space, the sequence of elements of the space converges in the norm of the space to U. And the norm of U squared is just the sum of the squares of these real numbers here. Conversely, if you have any sequence in little L2, the space of square summable sequences of real numbers, you can construct the series alpha k Ek. Again, you can construct it like this, from K1 to n. So this series will converge in the norm of the space to a certain element U, and this U will have this property. Okay. So essentially what I'm saying here is that if you have, if your space H has an orthonormal basis, you have an isomorphism. So this H is isometrically isomorphic to L2. This is isometric. Any element H you can associate to a sequence in L2. These are the coefficients. And any sequence of coefficients in L2, you can associate an element in the Hilbert space like this. Okay? And the norm in the space of sequences is the same on norm on the Hilbert space itself. So the next theorem that we're going to prove, after we prove this one, is to actually show that any separable Hilbert space has an orthonormal basis, because this theorem depends on the space having an orthonormal basis. Okay? So every separable Hilbert space is essentially little L2. Little L2 is essentially the only one that there is. Of course, we don't work all the time with little L2. We have other separable spaces, big L2 or sublog space or anything, but it's not very convenient all the time to express things in a basis or express any sort of operator in a basis. Sometimes it's just better to work in the spaces themselves and express your operator as an integral operator or something. You know, if you express in a particular basis, it gets actually very messy. So this is useful, but it's not by any means the end of the story. Okay. essentially, the proof is essentially a corollary of what we already did, right? How would I do this? So being an orthonormal base essentially means that this space En, like being the real span of each En, these are mutually orthogonal, and their span is dense in the space, right? So these guys are like we had in our previous proposition. Let's just prove that in this setting, the projection over U on En, you can just look that this is just U scalar E projection over Ek. It's just U scalar Ek times Ek. The projection of U over this subspace of dimension 1 has to be a multiple of the generator. This is just the right coefficient. Right? Okay, if you wanted to verify this, so remember, all you have to verify is that U minus projection of U on Ek has to be orthogonal to every guy in this subspace. But this subspace is generated by one vector, so it has to be actually just 0 if you do the inner product with the generator of the space, Ek. But this is actually true, right? This is U minus, this guy is just lambda Ek. This Ek is 0, if and only if this lambda that you're getting here, U Ek, is just lambda Ek. It's just lambda, because this is 1. So if lambda is this factor here. Okay, so this is actually the projection. And we are done. I mean, this from the previous statement, the sequence of projections here converges back to U. The norm of U squared is the sum of the norms of these guys, which is just this number squared. Okay, so pretty much follows from the previous result. Is that okay? At least this part, right? This first part. Now let's take a look at the second part. Do we have anything else to do? Okay, let me give you a sequence in little L2 and try to do this series. So you can essentially, for the second part, if alpha n in little L2 is given, you can construct the sums Sn, which is just the partial sums, alpha k, Ek, from 1 to n. These guys are on the lemma that we proved before. These are my vk's. They're mutually orthogonal. The sum of the norms of vk squares is convergent. And so this in the previous notation is like these were the vk's. The sum of the norms of the vk's, just the sum of the ak's, which is finite, because the sequence is literal 2. So we know that this guy converges to somebody, to some S. Okay? So this guy converges to somebody, let's call it U. The norm square of U is the sum of the norm squares of the VK, so this we already have from the lemma. So as n converges to somebody, let's just call it U. We have this, we have the norm of U squares, the sum of the VK squares. It's the sum of alpha k squares. And moreover, U scalar Ek is just alpha k. This is essentially because of the property that if you just do the inner product of, say, for n bigger than k, n bigger than m, if you do Sn scalar Em, you get alpha m, right? So if Sn would be, you would have summands up to n, m would be one of them. If you just do the inner product, you would just get alpha m. And now you just fix m and send n to infinity. What you get is that the limit is U, scalar Em is alpha m. Okay. Good. So this is pretty much a sum up of the basic theory of Hilbert spaces. Whenever you have a basis, you can just project. You have an orthonormal basis, so you project on each direction and you have Possible's theorem. Good. Questions so far? This might have been the easiest class of this course, I believe. Everybody who knows linear algebra essentially knows these things. But just for completeness, this book of Brazil, it's not about order of difficulty, okay? So perhaps the first chapter, the very first pages of the book, if you actually open this book and read for the first time, you might get a bit scared that on page 2 the guy's invoking Zorn's lemma to prove Rampana, so it's very abstract. But the most concrete stuff and most elementary stuff about Hilbert space comes right after, chapter 5. By chapter 5 you're already, if you have gone through the book all the way up to that, you have learned so much more difficult stuff that this might be a piece of cake chapter compared to the other ones. I don't know how you feel. Yeah, the first time that I looked at this book when I was about your age, it was a bit scary. It was a previous version of this book. It was not even this English version with the exercises.
It's a French one?
He has a French version, which is essentially just a bunch of lecture notes with no exercises and stuff. So it was in French, and there were no exercises, so it was kind of a bit more, even more frightening for someone who does not speak French like me. So, okay, so to conclude, let's prove this proposition here. So every separable Hilbert space, which essentially is going to cover all the situations that we work, has normal basis. And again, the proof is not very complicated. Just follow the natural steps. If the space is separable, you let Vn, when 1 to infinity, be a countable.
You can use Gramsci.
Yes, that's what we're going to do. Countable and dense subset. You start with any countable and dense subset. And what you do now is you take the subspaces generated by these guys. So let's just start and say F1 would be the span of V1, F2 would be the span of V1 and V2, and say Fn would be the span of V1 up to Vn. You can take spaces like this. It might be that, so when you construct it like this, you obviously get some inclusions. This guy is obviously containing this one, which is containing this one, but there might be some guys that are equal here. Okay? So you just start like this. So just choose, and now you just go through some sort of algorithm to finish the argument here. So just choose E1 belonging to F1 with a norm of E1 equals to 1. This is your first guy in the basis. And then you go, if F2 is different from F1, if you're not the space, this means that you can choose a guy which is orthogonal to E1, right? And then you choose E2 such that E2 is orthogonal to E1 and E2 is just here. Okay? And then you keep doing this. If the next space is equal, you do nothing. If it's bigger, then you choose one guy which is orthogonal to all the others. How can I choose? Once you have completed k steps, you're going to choose the k plus 1 step. If you have a space which is not the only one, how can you choose one vector which is orthogonal to all the other k before? So you just choose one random vector which is not in the previous space, and you subtract the projection over the previous subspace. Therefore you get, and then you normalize it to be 1. So this is the Gram-Schmidt diagonalization process that you learn in linear algebra. So the spaces generated by these EIs are the same as this, so it's clear that this E ends here is the required set. Okay, and where we have used, so by construction these EJs here are orthogonal and have always norm 1, and the fact that they're dense comes from the fact that this sequence Vn is dense. Okay, good. Let's see some examples of this. Who can give me an example of this in an infinite dimensional subspace? Of this thing. Little L2, right? Little L2, you have, of course, a basis. How about this space here? L2, so examples. Let's just try to think about some examples. Little L2, that's okay. That's the only example that there is, right? So you can just take, of course, En to be the 0, 0, 0, 1, and then 0, 0, in the position N. Give me another example. How about this one? L2 of the interval 0, 1. Right, so these are the functions f from 0, 1. You can put closed if you want. Doesn't matter. To R with the integral of f of x squared dx from 0 to 1 finite.
We need to define the characteristic functions with rational endpoints.
From 0 to 1 of it?
I mean, we take the characteristic functions over intervals with endpoints rationals, but they are not necessarily orthogonal.
Okay, so let me. Maybe I should. Let me change a little bit and let me consider like complex valued functions. Complex valued theory would be just the same, okay? So let me get to the base of functions that we're going to use to develop the theory of Fourier series. So what's the usual basis for these guys? So the usual basis is these functions. The so-called Fourier basis. Here is the functions of the form e to the, from 0 to 1, let's just say, if 2 pi I, just call it e k to the e to the 2 pi I kx. Let's just call it this, when k is 0. Okay? So these are my elements. These are all elements in this space. Okay? They all have, they're just complex numbers of absolute value 1. So when I integrate from 0 to 1, they're modulus, this is just 1. So of course, the norm of this AK is like this. So AK is a bad name. So let's just call this functions phi k's. I don't know. So the norm L2 of this phi k is obviously 1. Check. Phi k scalar phi L. What is this? Just the integral from 0 to 1 of e to the 2 pi I k minus Lx. Remember that the inner product here in the complex setting f against the inner product here is just f against g bar. So if I do phi k scalar phi L, it's just e to the 2 pi I k minus L. Yeah. And this is, well, this is just the integral of cosine of 2 pi, cosine 2 pi k minus Lx plus I sine 2 pi k minus Lx. So if the integers are not the same, if I integrate cosine over a period, or if I integrate sine over a period, this gives me 0, right? Gives me 0 if h gives me from L. So they have norm 1, they are orthogonal, they are almost what I want. I just want to conclude now that the subspace generated by these guys is dense. Okay, so check here. How about dense? How do I do this? How do I argue that this is dense?
So they are dense in something we know that is already dense.
That's a good start. What do you know about these functions and where they are dense at?
Continuous function.
They are dense in the continuous functions with the sup norm. By which theory?
I think it would be Fourier.
No. No, you have done this. Hmm? Well, yeah, Moon's theorem, but this is even a weaker version of Moon's theorem. Moon's theorem is too much, right? This is just plain and simple Stone-Weierstrass theorem, right? So what did you have in Stone-Weierstrass? Can you remind me? So Stone-Weierstrass, you needed an algebra of functions, right? You need an algebra of functions, so I'm going to take finite linear combinations of these guys. This is an algebra, I can add them up, I can multiply them up, so whenever I multiply them up, I still fall in the algebra. In the complex case, I need my algebra to also have the conjugates of the functions, but having the conjugate is just changing k to minus k, so this is why I put k integer, not just natural. So this is an algebra of the finite linear combinations of these guys. It's an algebra of functions that is closed under complex conjugation, and that contains separates points, right? So why does it separate points? This is a good exercise for you to try. So if I have 2 points, I can construct a function which is different on these 2 points. Think about it, it's not hard. And then it contains the constants, right?
Yes, if it contains a constant, then it is dense.
It contains the constants because the constant is just the k equals 0. Okay, so think about why this algebra separates points. It's not hard to given 2 points, construct a function with these guys that the value is different at the 2 points.
Just k, we can take k equal 1, it separates all the points. It is injective.
K equal 1 is injective from 0 to 1.
It may be except
pretty
on
much.
0 and 1.
Yeah. Okay. Yeah. That's not hard.
Other points.
Okay. Okay. You guys nailed it. You guys are.
If x is 0 and 1, you can separate.
Hmm?
If x is 0 and 1, then x and y is 0 and x is 0, y.
No. Well, in theory. Okay. So let's. Okay. If you want.
No, but then we can't use.
Yeah. Okay. So that's true. That's true. So.
No,
Okay, so
because
let's
we
do
have
this.
the constant, it separates all the points. Have the having no. Of course not.
Now, these functions, they all take the same values at 0 and 1s, yes. So, yeah, so you cannot separate the points 0 and 1. Okay. Okay, so maybe what we need is a we could, well, because this space, yes, how do I want to say this? Yeah, you can take of 0 and 1 here being the same. You can take the functions on the circle. Your compact k being like the circle, if you just identify 0 and 1. So let's just go with this with this notation, right? Because but there are, or if you want to go through a slightly different version of the Stone-Weierstrass theorem. So if the algebra doesn't, if 2 points always have the same value, then the closure is it's closed on the space of continuous functions that attain the same value at the 2 points. But this is what or maybe I'm doing something wrong. So I wanted to show that this is dense, right?
But consider the same as a maps on the circle solves the problem, as you mentioned.
L2 of 0, 1. No, but in principle, my functions could have two different points at the. So these functions are all continuous. Yes. This is not what I. This is not what we. Because at the end, I would like to approximate, say, a function. It could be okay if I wanted to approximate a function that does this, right? I could try to approximate this function by linear combinations of these guys. The funny thing is that linear combinations of these guys, as you point out, will always have the same value at 0 and the same value at 1, right?
This function is always.
No, but there is one point, because we are considering them as elements of L2, we don't care about their value of, at a set of measure 0.
Yes, but.
So we can consider another function which gives the same function, this phi k, but which at 1 gives the value 3 or whatever. It is the same function as an element in L2.
Yes. But these functions will always, what I'm trying to say is that if you try to approximate this function by linear combinations of this, will always be something that does like this. You know, you're going to get, in the L2 norm, you're going to get small, but let's see, how would you argue with your Stone-Weierstrass? Okay, so what we need is algebra of functions to be closed, to be an algebra of functions, closed under conjugation, separates points, and perhaps, and that's it, right? And contains the constant functions. So, I mean, we could argue that this is, okay, so this is dense in the continuous functions. Let's put just 0 and 1 minus epsilon. Let's see. For any epsilon, this is dense in the interval 0, 1 minus epsilon. Now we're okay? Okay, but it's dense in the sup norm. It's dense in the sup norm. So now let's remember, I want to prove that the finite linear combinations of this guy is dense in the L2 norm. Okay, so now, okay, so let's just see. So now take any f that belongs to L2 of 0, 1. Okay?
Actually, I just have a small comment. We can just renormalize this wk so that they don't attain the same value at 0 and 1. Just make the period a little bit longer. For example, if we make the period of the function 2 pi.
But you have to be careful not to destroy this thing.
We can put a constant. We can divide by some value to make the norm 1.
Norm 1 is fine, but just the orthogonality.
It
0.
will be still orthogonal because I will just multiply by some factor.
Well, this is the same thing that I'm doing here. Just multiply by a factor 2,
Yeah.
make my interval smaller.
Yeah, in fact, I'm just saying we can do it the other way so that we keep the interval 0, 1.
Anyway, I mean, I'm sure you can find as many, you can work this out in many different ways. What I'm saying is that let's get a linear combination of functions like this that gets close to any L2 function. So what you're going to get is, you're going to get, say, so take any f in L2. So suppose we want to find f minus a certain g, when g is in this linear combinations of this guy. So g is just the sum of ak e to the 2 pi I k x, and k from minus n to n is a finite linear combination. Is a trigonometric polynomial, right? And I want to find f minus g when the norm L2 is less than epsilon. Okay, so I'm giving you epsilon. This epsilon is different. So let's just say for any delta I can find. So given epsilon bigger than 0, I want to find g such that this happens. So what you would do if your f is given, you will just say choose first delta such that the integral, say from 1 minus the delta to delta of f is very small. Okay, so of f of x square is very small, so less than epsilon over 2. Is that good? Well, I gotta be careful. I gotta be careful here. I gotta be a little bit careful with what we want to do. So I just wanted to get my function here, boop, boop, boop. And I wanted to say, okay, this function f is given. It has a little mass here, and this mass is small. And here in this set, I can approximate by one of my functions very nicely. So here I can approximate in that infinity norm, hence in any sort of L2 norm. But then I would have a problem in this space because this function here could be, when I do the L2 norm in the whole thing, in principle it could be here. And then this could create a big mess. So this is my problem. Right? Do you see? The idea that I was trying to do is that I wanted to make my interval 0, 1 a little bit smaller, say 1 minus delta. And in this interval 1, 1 minus delta, I can approximate my f. I can approximate my f by a continuous function, and I can approximate this continuous function by these guys, right? Maybe I want to do something different. Okay, so how do we fix this? Maybe this is not the way to go. I mean, let's massage a little bit. Let's find a way around this. Can I, for example, okay, you guys are okay if my space, if I just identified 0, 1 in the circle, and if that were my compact space, I could approximate any continuous function on that space by a function like this, in the sup norm, right? So perhaps we should try to, given any f in L2, which may not have the same value at the endpoints, or may not have, I'm not just talking about pointwise value, but the function may have some values here. Wow, this stroke is horrible. Some value here and some here. Can we approximate this function in the L2 norm by a continuous function that has the same values at the endpoints? This is perhaps what we should do.
Sorry, can you repeat the question again?
Okay. And this might be good. Might be a good solution. My question is, and see, this is actually very instructive to me, and I hope it is to you. Because this is how we do these problems in real life. We try to do something, we know what we have to use, there are some problems in the way. We try to go and enter here and it doesn't work, we try to enter there and it doesn't work, and try to enter there, it doesn't work. You see the problem here, right? So with this theorem, with the theorem of Stone-Weierstrass, I can approximate continuous functions in a compact set in the sup norm, in the norm of the continuous functions, by this algebra of functions, right? And then somebody raised a point to me. Well, this algebra function is good, it's an algebra function, it's closed under complex conjugation, it contains the constant, but it does not separate points, because at the endpoints, the functions are always the same. That is true. Okay, so how about we don't look at the interval 0, 1, but we identify these 2 points, and we imagine like functions, continuous functions in the circle. That's okay, right? Our compact set K is now the circle. You can take continuous functions in the circle, and then you can approximate in the sup norm by any guy in this set now. It's just thinking that the points 0 and 1 are the same. Okay? But to think about the continuous functions in the circle, you can either think, okay, so there are 2 equivalent ways to think about this. You can either think about the continuous function in the circle, or you can think about the continuous function in 0 and 1, who has the same value at 0 and at 1. So you can identify with the function in the circle, right? Okay, so if my compact set is 0, 1 modulo the equivalence relation that 0 is actually equal to 1, or the circle, I can talk about continuous functions in this compact thing, which is just the circle, or the continuous functions on 0, 1 that have the same value at the endpoints. Now, a function like this, I can approximate in the sup norm by this algebra. Is that correct? Good. But this was not my original question. My original question was, how can we approximate any function in L2 of 0, 1 in the L2 norm by a guy in this algebra? Okay? So this is just a step in between. So what we have to do, actually, is to start with the function in L2 and approximate good in the L2 norm with a continuous function that has the same value at the endpoints. For example, 0. But it seems to me that this is reasonable, right? Because if you get any sort of function in L2, crazy as it is, you can approximate by a continuous function that is 0 at the endpoints. You could just start here and just... and then, it doesn't seem to be too much of a problem, right? So the idea is start with any L function, and then you approximate by a continuous function in the L2 norm that is 0 in the endpoints, and then you approximate this continuous function by some guys in that form. Okay? Does this seem a reasonable plan to you? Now let's just make this formal. Okay, so let me forget here. Stone-Weierstrass will give me that. By the way, there may be many more different and easier ways to do this. But in the spirit of our discussion, let's just finish this proof. This is what I like about analysis, is that there's no one unique way to go. Depending on where your conversation goes, you can always find a way to find the objective. So let's see. Stone-Weierstrass will give me what? Will give me that this span of e to the 2 pi I kx, and k is an integer, is dense in the continuous functions of the circle. Do we agree on that? Or continuous functions in the space 0, 1 modulo the equivalence relation that 0 is equal to 1. So this means like the space of f from 0 to 1 to C continuous such that f of 0 is actually equal to f of 1. Okay? This is the space of continuous functions such that f of 0 is equal to f of 1 is a Banach space with the sup norm. To say that f of 0 is equal to f of 1. If I add two functions, this is a vector space. If I multiply two functions by a scalar, this is still good. And the sup norm is just the space of the functions in the circle. Okay? Of course, this is a subspace of all the continuous functions from 0 to 1. Is that okay? Yeah. Okay. So this is what this theorem gives me. Now, take any f in L2. I want to approximate in the L2 norm by a function in here. The first, I will do this in two steps. First, I will approximate f in L2 by a continuous function that is equal at the endpoints, and then I will invoke this theorem. Approximating f by a continuous function that is good at the endpoints is not a big problem. Is that so? I can just you guys already have the analytical maturity and the tools to do this. So if you have a function f that lies in L2, and whatever it is, right? This is your f. What you could do is you could just truncate here and here. So you just erase what it was before here, and you erase what is after here. So just erase. let's just consider, say, f epsilon to be f times the characteristic function of the interval epsilon 1 minus epsilon. Okay? So it's clear to you that f epsilon converges to f in L2 as epsilon goes to 0. Okay or no? Is that clear? That is clear, right? Because the difference is just a piece of the original f in L2, which obviously goes to 0. Okay? Remember, the difference of f minus f epsilon in L2 is just the integral of f in L2 in these intervals 0 epsilon union 1 minus epsilon 1. Okay? Now, f is in L2, f squared is in L1, and you might have learned in measure theory that if I have a function in L1, their integral is absolutely continuous in the sense that if I integrate over small enough intervals, this interval goes to 0. Okay, so this goes to 0.
Actually, we can do even something more simpler. That we need only to approximate continuous functions in the L2 normal by continuous functions which have the same values at the endpoints. Because whatever, if I am given a function f, I can approximate it by a continuous function, and this continuous function itself I approximate it. And
yes.
In this case, we can use the mean value theorem to show that this limit will be 0. Because
this limit here?
No, this limit here. Because now f and f epsilon will be continuous functions.
Yeah. Yeah. You can first approximate f by a continuous function in L2, then you can approximate a continuous function by a continuous function that is 0 at the endpoints. Okay? Whatever you want to do. So what I'm saying is that this is not hard to do, right? So this is first step. So approximate f. There is epsilon such that the difference between f epsilon and f is small enough. Okay? And then now you have a function which is the support is away from 0, 1. What you can do is now choose this epsilon bigger than 0. Choose this epsilon 1. That is, well, you should do things behind that. I have to give you the epsilon first. Okay, so I'm going to give an epsilon bigger than 0. Blah, blah, blah. I should perhaps not call this epsilon. Let's just call this epsilon 1, epsilon 1, epsilon 1, epsilon 1, epsilon 1, blah, blah, blah. So now, then you can, of course, choose epsilon 1 such that, say, f minus epsilon 1 is less than epsilon over 5. I don't know, whatever. So you got a function that you just cut the support a little bit. Now, what you can do is then you can take this f epsilon 1 and start doing some sort of approximation of the identity with your favorite kernel, phi epsilon 2, right? And send your epsilon 2 to 0. So just take phi, your favorite approximation of the identity. Phi is a C-infinity function with compact support. With compact support, this is important. Okay? Now, if you take a function which has compact support and another function which has compact support and epsilon 2 goes to 0, remember the support will just be the sums of the supports, right? So if this function here is at a little distance from 0 and 1, the support, and epsilon 2 is small enough, when I add the supports, I will still be away from 0 and 1, right? So I know that when epsilon 2 goes to 0, this goes back to f epsilon 1 in the L2 norm. But now this function is continuous. What I'm essentially saying, I'm approximating f in L2 by a continuous function. This is how we do it, right? But this function has still is a continuous function, and 0 at 0 and 1. Right? Good. So what I'm going to do now is, okay, so choose epsilon 2 such that f epsilon 1 minus f epsilon 1 convolution with phi epsilon 2 in norm L2 is less than another epsilon over 5. This is a 5. Okay? So you are now very close to the end. So now what you have is what you constructed was a continuous function that lies very close to your original function here. So this is a continuous function now. That is 0 at the endpoints, because this is how you construct it, right? So the idea behind this is very simple. First, take your original f, truncate it, very close to the endpoints. Now you modify a little bit, but not much, so you still get 0 at the endpoints, and you get close. And now you have a continuous function, and then with this continuous function, what you can do is you can...
I have a question. The choice of the function by which we will convolute.
Any function with compact support.
But why the support of the convolution will be far from 0 and 1? Because if the support of...
The support of f convolution with k is contained in the support of f plus the support of g. You have done this exercise, right? So if the support here has a room of epsilon, and if the support here is finite, okay, say 100, let's just take 1 for simplicity. Just take a function with support 1. So phi epsilon 2 will have supporting epsilon 2. So if support, this is the approximation of the identity, right? So you just choose epsilon 2 very small. For example, epsilon 1 over 27. So you just go, instead of going the full epsilon 1 to the right, you just go epsilon 1 over 27. You have 26 over 27 to go. Okay? Okay, so now you're done. You got this continuous function g, and then you can approximate this g. This g is just that f epsilon 1 convolution phi epsilon 2. Let's just call it g. So there exists h, which is just the sum of trigonometric polynomials of this sort, such that g minus h in the sup norm is less than epsilon over 5. But then the sup norm, then the L2 norm, then I just use the L2 norm, it's just the integral of g minus h, L2, right? It's less than, yeah, whatever, this is, epsilon over 5. Okay? I don't know, it doesn't need to be, because actually take square roots. So, the L2 norm is less than the L infinity norm, of course, right? It's less than or equal than that. Okay, now you just add this line, you just add this line, and you just add what? This line. Okay, so this h is close to g, this g is close to this f epsilon 1, and this f epsilon 1 is close to f, all in the L2 norm. You add them up, 3 epsilon over 5 is less than epsilon. Okay? So we have proved that this usual Fourier basis is actually an orthonormal basis in the space of Hilbert functions, in the Hilbert space of L2 and 0, 1. Is that okay? As I told you, this by far might not be the only proof. There are more direct proofs by showing that these functions are...
Under what conditions this convergence is pointwise? Because this convergence is...
Which convergence?
The Fourier series to f. It's just converge now into, right?
Well, we haven't talked about Fourier series yet. I'm just saying that these special functions form a basis, right? Yeah, okay, but now, okay, so anticipating your question, now any function f in L2 can be decomposed in this basis, okay? The coefficients are called Fourier coefficients. The sum converges back to the original function in the L2 norm by the theorem that we just proved. It was for a long time an open question to see whether these partial sums converged back to the function pointwise almost everywhere, was open for 30, 40 years, and it was finally solved by Carlson in 1966 in the affirmative. Like actually the Fourier series, they converge pointwise almost everywhere to the value of the function f. This is the result that gave him the Fields Medal in 1966. The pointwise convergence of Fourier series to the original function. Okay? Alright, so I hope this was a bit enlightening. We'll talk next class, next two classes next week. We're going to talk a little bit about the Fourier transform and the Fourier series, and we're going to be seeing a lot of this. Yeah, I think I'll stop here today. I wanted to talk a little bit about Lux-Milman theorem, but maybe next time. Let's stop here, and we'll continue next Wednesday at 11 a.m., okay? Next Wednesday at 11. See you guys.